The Institute for Tribal Environmental Professionals here at NAU is working with the U.S. EPA's Office of Environmental Information to promote tribal involvement in the NEEN, the National Environmental Information Exchange Network, and as part of that work, hosts annual Tribal Exchange Network conferences. The following webinars were presented at the 2017 Tribal Exchange Network Conference in Viejas, California by John Warren, Senior Statistician at EPA, and are invaluable resources for just basic concepts and common sense statistics.
Okay, this is a calibration problem. And there were 4 technicians, and they're doing the same analysis. And there's a controlled variable, there's a measured variable. The skilled at what they were doing. And so what they did was they did all their work. They had the same number of analyses, as you can see. And then they put it into a statistical program. Some of these programs are just, there's no brains. All you have to do is pour the numbers in the top, crank the handle, and out comes all the bottom. And would you believe that within rounding error, they all had the same results? Now, I must say, their boss was quite pleased, because after all, when you've got a whole load of technicians working, one of the things that you want is the fact that they should all be consistent. And that is pretty consistent. Look at some of the things there. Look, residual sum of squares. You've got to love that. It doesn't mean anything, but you've got to love it. When in doubt, use a lot of statistical terms, right? Nobody else understands them, so, get away with murder. Then the boss's wife said to him, "Are you sure?" He says, "Oh, look, there it is. Here's the proof." And then she said, "Did you actually plot the data?" And he says, "No." Oh dear. Does that 4 data sets look like anything similar? If it does, please take a deep breath, take your glasses off, because, quite frankly, there's a huge problem. Now, the whole reason is, let's go back a little bit. Look at that. What does the human brain do when it's faced with an array of numbers? It goes on the fritz. It starts saying, "Oh yeah, right, yeah, numbers, yeah." By the way, it works for statisticians too. We suffer from it as well, all right? Because, quite frankly, the human brain is not well wired to deal with numbers. But the human brain is very well attuned to pictures. Numerically, everything looked wonderful. In reality, what would you say? What would you say about this fellow here? Was he working?
No.
Yeah. Hello. What about this guy? Did it worry him? Wouldn't you be worried? So we definitely do have a problem. All right. First of all, just let's get rid of things. All right. Let's get rid of the definition. What is statistics? Well, if you ask most college graduates that question, what is statistics, you will get a magnificent yuck, because very few people like statistics. Even mathematicians don't like statistics. And that's why if you really want to insult a mathematician, call him a statistician, and then vice versa. If you want to upset me, call me a mathematician, because I'm not. Right? It's one of those weird grey areas where the interpretation becomes part of your skill. So a statistic is a numerical summary, all right? Like a mean, or you've heard of a standard deviation. That's a statistic. Statistics is the science, and statistical methods present information to a manager in a useful form. Why did I use this word here? Why that? Well, come on guys, you're expected to be the expert. So as you are expected to be the expert, you are expected to understand it. But the key thing is, can you make the next layer up understand it? there is the skill in things, because you can quote all these statistical things, but making it in a useful form so a manager can understand. And by the way, are managers very smart?
No.
Well, that was an excellent answer, a very fast answer too. Yeah? No, managers, they don't think like us. They've got different things they want to worry about. And quite frankly, if you go and try and talk science sometimes to a manager, you're talking to a blank wall. It won't work. So you have to go to their length. One of the things is using pictures can really, really help. All right, so the objective is actually then to learn from the data and be able to interpret these features that you've got from data. And this interpretation is going to depend on several things. And there's three of them at the bottom there. Take a look at those last three. What would you say is the most important? Go on, there's no wrong answer.
The third one.
Third one. Excellent choice. The context. I mean, you say, you can have all sorts of wonderful things, but if it's taken out of context, what is it going to do for you? Nothing. But also the second one is going to be important too. What assumptions did you make when you collected that data? And you talk to some people and they say, I didn't make any assumptions. You say, yes, you did. You assumed that you were collecting data on what you really thought you were collecting. You thought that the individual values that you were getting made sense. And so it depends on what assumptions and obviously the method that you use to summarize this data, to squeeze it into a meaningful form. The context should include the big picture. You notice I've said big picture, and then next to it, in brackets, conceptual model. You see, when you go out and collect data, you don't just blindly go in there, right? You actually do a very intelligent thing. Even if you've never been trained in some areas, you will go to it in a logical fashion, wouldn't you?
Yes.
Wouldn't you?
Yes.
Yes, of course you would, because your life is very logical, and so you go into it on a logical fashion. But actually, what your brain is doing, your brain is actually working out a conceptual model. After all, if you're going to go and investigate some contamination on a site, would you go near where the exit pipe is, or would you go to a nice safe corner where the cows are grazing? You say, well, obviously I go to where it's coming in. In other words, your conceptual model is that contamination is coming in at one end, and then it's doing something, and you want to find out what it's doing. So having a conceptual model, right, is a nice fancy way of saying what common sense idea of the big picture do we have. And it's a great word to use, by the way, conceptual model, right, that unnerves managers. All right? It unnerves them because it means that you know much more than what they thought you knew. Because a conceptual model, right, immediately turns around and says, well, aren't we talking about reality? Well, reality is very, very complex. And the way we deal with it is to smooth it down into a model, a conceptual model that allows us to deal with complex problems. And without context, interpretation loses both its scientific and its realistic basis. So just because someone says, I collected data, I did this, I did that, I did the other. No. Why did you do it? How did you do it? And now I'm now going to do the blood oath with Melinda. How did you work out your quality assurance project plan? And quite frankly, because that, in a sense, gives you the conceptual model that you need as a basis for moving. All right. I'm going to show you three different methods of summarizing data. histogram, scatterplot, and a box plot. Now, is any one of those better than the other? No. Depends on what you want to show. What do you want to demonstrate? So let's have a look. Okay, here's the data. And by the way, for today's presentation, I'm putting everything in terms of a hazardous waste site. And there are two reasons for it. I know that you guys do a lot of monitoring, but I don't want to get tangled up by misusing a certain method, because I ran into this years ago. I said that I used a method to collect monitoring data, and immediately the hand shot up and said, was there a VX105 used? I couldn't answer him. So what I'm doing is I'm deliberately taking a hazardous waste site that has the advantage that visually you can see a hazardous waste site, and we can pretend out there, right, where the guy's shooting stuff, right, is a hazardous waste site. And so when you talk about we'll go out and take samples, it's easy for the brain to turn around and say, oh, I got it, I get it. And here it is. Here is 100 random samples from the Midway Municipal Site in PPB. And I know you guys have seen this dozens of times. Does anything leap out at you? No? Why not? Because the brain is being tortured with all these numbers. I mean, it's being held up. So let's trim away some decimals and see what happens. Is that any better? All I did was get rid of the second decimal place. All right. Well, let's do histogram. Is that particularly useful? No. Got lots of holes in it, doesn't it? Got lots of holes. It might be beginning to look like something you might recognize, but, well, tell you what, let's round it off to the whole number. All right, now look at that. Throw away all those valuable decimals. All right? Is that any better? Hey, look at this, guys. Look at this. Does that look like something that statisticians love to talk about?
Yes, standard bell curve.
Standard bell curve. Exactly right. Exactly right. The standard bell curves are nice because we know a lot about them and we can deal with them. That's why we love to see standard bell curves. Well, now, if rounding them off to the nearest number was good, right, and an improvement, let's round it off again. Right? I mean, we're wrong. Yeah, well, so much for being on a roll. All right? In other words, look what's happened. Let's go back just for a second. That made sense. That didn't. And obviously, if you turn around and say, well, let's round it off to the nearest tenth, what do you think is going to happen? Just got one great big pillar in the middle, and that's totally worthless. All right? So what are you going to say here? Okay, here's your rules for histograms. First of all, try out different sizes for the histograms. They call them bins, as in you're going to bin things when you've got a whole lot of data or a whole lot of things coming through. You put them in different bins. Try different bin sizes to see what happens. Next thing, make the bins equal in width and touch each other. Now, if I wanted to sort of be very, very erudite, I would say, make sure the bins are equal in width and contiguous. But then people sort of start wondering, what is a contiguous? Make them touch each other. And you say, wait a second, is that a histogram then? Is that a histogram?
Yeah.
No. Why isn't it a histogram? Do they touch each other? No. So actually, although many people who don't understand things will call this a histogram, it actually isn't. It's actually a bar chart. And you say, well then why is it so important to have them touch together? Because if you touch them together, you can actually use statistical theory to form what's called probability distributions that will help you, understand the data even better. So, and I obviously did this deliberately, right? Because, I tell you it's a histogram, and you're not going to turn around and say, wait a minute, John, But actually, it's actually a bar chart. Now, the reason why it's important is because you can actually try and fit different distributions to the data set. And the two most common ones that you will find in environmental work is a normal, which is a bell-shaped curve, and something called the log normal. And a log normal looks like a bell-shaped curve, but it's anchored at 0, and it looks like an elephant sat on it, on one end, because it goes up, and then it comes down. Right? And what it's actually telling you is if you took the logarithm of the data, the logarithm of that data would be nice and bell-shaped. And we use that a tremendous number of times. But this is the key thing. Look at that visual impact. Look at that visual impact. You see how those great 100 data points all of a sudden could be coalesced into a pretty picture that could be easy to explain to a manager. This is what we got, boss. Right? And now I'll tell you a secret. If you really want to confuse people, make sure there's about 5 or 6 decimal places. All right? Because you see, the brain just sees all these things. It forgets about there's a little dot, meaning decimals. And so you want to confuse because you're worried, make sure you get plenty of decimals in there. I mean, nobody will catch you, all right? And you're not lying, you're just giving an interpretation. All right, what else have we got? Well, here we go. Let's look at scatterplots. Here's 100 data points from the Comstock Air Monitoring Station, 100 consecutive days in summer 2005. Look nice?
Yes. No,
Yeah, it looks lovely. Look at that. We've even got the dates in there too. And that shows you how careful I am. Well, look. Does that tell you anything?
Does you get connected back?
But supposing we turn around and do something different. Supposing we rank them from smallest to largest. Here we go. The minimum is 37. There it is. The maximum is 66. And the range, which is simply the maximum minus the minimum, right, is 29. Let's plot that. Let's see what happens. There's the data, all 100 points, from lowest to highest. And here's PPD. Now, obviously, why is some of these much fatter?
More days than that.
More data was actually, it was sort of like for this one here, perhaps there was 49 that occurred 3 times. Well behaved. Well behaved. Statisticians love this. Love this. Here's a $50 word. Right? Stand back, here it comes. Sinusoidal curve. Now, if that's not worth $50, that's worth the cost of entrance alone. I mean, come on. Sinusoidal curve. Beautiful symmetric tails, right? Smoothing here, all right? And we like that. Don't forget, data are just like children. Well-behaved ones, we appreciate. Badly behaved ones are a problem. Just the same for us, yeah? All right? Well, let's look at the Lode air monitoring station. It's over the same period. What does the brain do? Does the brain differentiate between that and that? No, it's just a mass of data, isn't it? I mean, until you start getting into it, right, it's just a mass of data. Let's do the same thing. Does it look a little bit different? Yeah, a bit different. oh, look at this. But when we get it, it's got the same maximum, it's got the same minimum, right? It's got the same range. What could be wrong? Let's have a look. This is poorly behaved. This is poorly behaved. You want to give a statistician heartburn, present a data set like that, because look what's happening. There's a whole lot in the middle that's not telling me much. And then there's a great increase at the end. Is this well behaved? No, it isn't. And just by doing a simple plot, you've made the ability to turn around and say, if it's well behaved, I can do things with it. If it's badly behaved, I'm going to have to go and ask for help. And so, have you done any math yet?
No, yay.
No, not a bit of math. Not a bit of math. We just got a pencil and paper. Isn't that great?
So the only difference between the well-behaved and the poorly behaved is that the well-behaved data set, the data points are more evenly distributed.
Correct, correct. Yes. And so in the well-behaved one, it would go up slowly here and then slowly rise and then go up there. So that's the difference. You're quite right.
So is that like the difference between the normal and the log normal?
Not necessarily, no.
That could be a monsoon in Arizona. Because your data could be just nice, 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 and then boom.
Right, and
Yeah.
you know what, that would mean there are two different distributions, actually. You've got your normal day distribution, and then you've got your Hadoop distribution.
Okay.
Yeah. And not only that, I'll tell you something, guys. Look at that. These are consecutive days. This is not a random sample. And what do you know about consecutive days? They sort of agree with each other, don't they? I know when we came here, it was horrible weather. But then it slowly improved, and today is pretty much the same as yesterday. Actually, a statistician would turn around and say, there's a lot of correlation going on here. Be careful with how you do this. And so, there's lots of things that you can get that you haven't even done any statistics with. So, what are we looking for? And this is exactly the point that she was making. Look at this. Nice, fairly large plateau, steady rises, no hiccups. And this afternoon, providing you haven't gone brain dead, we'll show you some actual statistical ways of identifying if there's been an outlier or something abnormal that is going to upset things.
But just to clarify, the points on those scatter plots were not consecutive days.
They're ordered by magnitude.
Days.
All right, what about box plots? You say, what a strange name. Well, if you look in the literature, they won't just say box plots, they'll say box and whiskers. You turn around and say, this is getting a little silly, isn't it? And actually, not really. Oh, wait a minute, I've heard of these things. Upper quartile, lower quartile. You guys that have got kids, you're forever saying, in what percentile are they working at? We come into using the word percentile all the time, don't we? Well, here we're going to turn around and say, what is the median? The median, by definition, is that value such that half of it is smaller and half is larger. And sometimes, if you want to be sort of nice and confusing, you can actually say, look, it's the same as the 50th percentile. In other words, the one right in the very middle. And what do they look like? There's a box plot. And you say, I have no idea why you'd ever want to use this. But they're very valuable. Very valuable. Because the brain gets so deadened by data, you have an opportunity to take away some of the deadening stuff. And what, for us, in the environment, what is the deadening stuff? The average stuff, right? Do we really care that sort of, shall we say, the pollution level is well below what it should be and all clustered around some value? No, as environmentalists, we are very concerned about potential anomalies that are very high. If we're dealing with pH, we're very worried about very small ones. And what box plots have the ability to do is block out all of the average kind of stuff and allow you to concentrate on the extremes. It's standard practice to put a line in the box to tell you where the median is, the 50th, and a cross is nearly always used to indicate where the average, where the mean is. If it was a very well-behaved data set, where would the mean be in relation with the median? It's the same, yeah. Because if you imagine a beautiful bell-shaped curve, the average is right in the very middle, and that's such that 50% less, 50% more. One of the things that you'll see is if there's a big difference between mean and median, it's telling you it's not a very well-behaved data set. Now, is this standard practice? Should be, but isn't. Depending on what statistical program you have, it might define this to be a different size box. And you can see now why they call it, there's the box, obviously, and these are the whiskers, and these are the dots. I mean, sometimes you wonder about the intelligence of people who name these things, but yeah.
What is IR?
That's the interquartile range. All right. What it does is it takes half of this and puts it here, and then half of it and puts it up the top here. And it, depending on what program that you have, it will actually define it for you. Let's have a look at the Comstock data. Here it is. It's been ordered from smallest to largest. The median is between the 50th and 51st. And so it's going to be in here. Where do you think the average for this? Come on, no calculating. It's a well-behaved set. Where do you expect the average to be? Pretty much close to the median, right? See, I'm trying to get you sort of to be happy with sort of playing with the numbers so that you're familiar with it. Let's have a look and see what it looks like. Now look at this. Why don't I call them just outliers? No. Bad. Naughty. Don't do that. I'm going to show you this afternoon that you can only call them potential outliers because I'm going to show you it depends on what you're assuming is going on. So when you do things like this, even though they may look, out of sequence or out of sort of natural, don't call them outliers. Call them potential anomalies or potential outliers, because you do not want to be nailed by telling someone, realizing that it's not an outlier, it's a real value, and your assumptions were wrong. Well, we're saying more about that this afternoon. So here we go. All right, there it was with the well-behaved data. Now let's look at the poorly behaved data. Is that a mess? Yep. Look at it, all spread out. So you see what it's done, well, the box and whiskers is block out that great chunk of data that we don't really care about and allows us to look more carefully at what's going on at the extremes. And that's useful sometimes because that's where our pollution problems are coming from. Eliminating the central mass by replacing it with a box enables us much easier to see what is happening. All right, are there other methods? Yes. Are we going to deal with them here? No. Stem and leaf, I personally don't like. Frequency graphs, all right. Ho, ho, ho. Hands up who's used empirical quantile plots. They're out there. It's a very specialized thing, and you possibly will not come into contact with it, but it's another way of displaying data. The last two are especially important when it comes to testing for normality, but that's a little bit more advanced than what we want to get to today. All right, what else should you be aware of? The bizarre. What's bizarre about that? What happened at 4 o'clock? What happened to 8 o'clock? Could that be a change in shift? Don't forget, we're watchdogs, and we have, shall we say, the dogs who are not necessarily on our side. And they may know that at 4 o'clock, with the change in shift, there's a great dumping program. And so, accidentally, we don't take a, after all, one shift is going off, new shift coming on. I mean, what could happen? Be careful, all right? Look for bizarre gaps, all right? Very important. How about preponderance of values? These are values from a Churchman smokestack. That's where they hold up a glass and they measure just how much is coming out of the stack. And if it's perfectly clear, it comes out as a 1. And if it's cloudy, meaning there's junk coming out, it can get all the way down to 0. Look at what they've got. By the way, this is the first data set I met with when I came to the EPA. It's probable they don't even do this now. Why are there so many 0.5 values? Well, think of my arm as being sort of like the meter. You know, there's 0, right, and there's 1. And you're looking and you're trying to estimate, and it could be, it's in the middle there somewhere. Oh, it's 0.5. Right? In other words, it's not a very accurate method. Be careful, because I had a contractor try and do this and turn around, you know, and I had to stop them and say, look, there's something completely wrong with this. Can you really distinguish between these values? Clearly, we can distinguish between 1 and 0.5. But can you really do the other values? So how reliable, ask yourself this, how reliable is that data set? You see how you start questioning by just looking at the data on. No math, no statistics, just actually looking at common sense. How about this? The bizarre. Too many decimals. What does the human brain say? The human brain says what? 12.9665. Man, that guy is on the ball. You know, especially engineers. Engineers love this. Engineers love this because they've got calculators that will calculate that many decimals. And you start to say to yourself, wait a minute, tenths, hundreds, thousands, tens of thousands. Wait a minute, what is this? What is this? Tens of thousands of ppm? What is the guy trying to do? Trying to convince you that because he's got so many decimal figures, they must be more right than the guys that have only got 1. Now, should you grin? Yeah, because the wool is being pulled over your eyes here because there is, you know, maybe no real reason for this. Engineers love this, seriously. So in conclusion, what do you know? A picture is worth, come on, all you Russians.
Billions and billions.
Billions. Well, you know, I actually did have a Korean one day in the class who actually sort of was able to pronounce that for. Well, that's, I think that's as good as, mind you, I don't mind that one. 10 to the 3, a picture is worth 1,000 words. And what we're trying to say is, yeah, the way to look at your data, turn it into a picture, because the picture will give it away many, many times.